Okay,
Perfect. Thank you very much, Cameron.
no worries. Okay, so thank you. My name's Cameron. I'm an F1 doctor at Worthing, and today my lecture will be about space medicine, more specifically, space agencies training program that they run once every year, more often than not in the and it is held in Belgium. So I'll be exploring space medicine, human space physiology, facing, and how it can trickle down into life on Earth. Background about me. So, like I said, I'm an F1 doctor. I'm currently in Worthing. Finished my cardiology rotation, and now I'm rotating to orthogeriatrics. I'm on the actual ward. I studied and attended this course while I was at the University of New York Medical School. So I was quite interested in space from a young age. So I've always been quite interested in space, but I never really found an intersection between space and medicine. Never really saw it as a viable career path for me. But then, browsing the internet, and I saw an article, a Google article recommended for me of the European Space Agency's Human Space Physiology Training Course. Essentially, what it was is a week in Belgium to Friday, 5 days, with a host of experts in the field of space medicine. They gave detailed talks regarding issues we faced, solutions for the future. During this time, we had a group project that we presented to experts, and we had time to get to know everyone because it was a wide cohort of people. I think I was one of three people selected from the UK. The rest of the class of came from Spain, Portugal, Greece, Norway, Lithuania. It was a real mix of people, many different people, not just studying medicine. So don't think if you want to get into space medicine in general, you just have to study medicine. It's quite an open field, and there's many pathways to get in. But the purpose of this lecture today is to explore the topic of space medicine because it is quite convoluted at times, encompasses a wide range of topics. So we'll go into briefly, and more specifically in this session, we'll discuss some insights from my learn about what was presented to me as the most important challenges we're facing and what does this look like in the future. So space medicine. The for space medicine is the study of how the human body responds to spaceflight, development of countermeasures to protect astronauts. And it really is just the second part of that countermeasures to protect astronauts. And why does this happen? So we need to think about what occurs to our body while we're in space. Well, on Earth, normal 1G gravity, that is our body's safe spot. But once we take the body into microgravity, what we consider an extreme environment, the human physiology starts to act a bit strange and doesn't really supposed to. So there are different responses depending on which you're focusing on, the bones, the muscles, the brain. And well, for these space medicine doctors, they go through each one and try and develop a countermeasure and to mitigate as much as possible any negative physiological responses. And so why does it matter? Like I was saying, it ensures the health of the astronaut during the missions, physiologically, and also it develops technologies that can benefit life on Earth. So it prepares humanity for deep space exploration such as the moon or Mars. Right now, we have the Artemis program, which is the sister to the Apollo program, and 4 astronauts back to the moon. And from there, as a testing ground and as a metaphorical launch pad of sorts, a trip to Mars, which is something we hope would happen within our life. The Artemis program, um, the landing on the moon should take place within the next few years, and then we'll be looking at that as a. So just to touch again on the course. So I was in my 5th year of medical school but we had people from years 1 and years 5, and in different degrees, from years 1 to 3 or 1 to. It was a real mix of people, and I think it just mattered on the abstract. Experience wasn't really required. It was actually favored if you had less. It was something that was more geared towards people looking to get an into space medicine who had never been exposed before. So, like I was saying, it's the headquarters in the Belgian countryside. It lasted 1 week. Saturday or the Sunday. Classes started on the Monday. We were given the second or third day, and from the Monday to Friday, we were having these lectures. What do we do? So we had a real wide range of experts and science, and topics ranged from increased intracranial pressure, protecting against radiation, to protecting against the psychological affiliation and high stress. And lastly, we presented our group project to a panel of experts, also fellow students. So first, I'll go over what we were trying to do, what we did, and our proposed solution. So essentially, the task was to understand negative physiological effects of microgravity in operating lunar. Now, microgravity and zero gravity are very similar terms that get thrown around a lot. I guess theoretically doesn't exist. There's always a small effect of gravity on the moon, which is a fraction of the Earth's, or Mars, which is different from both. So as we have gravity, we have the 1g on Earth, which we compare it to, but ISS, the International Space Station, there's always a tiny bit of gravity working. So understand the effects of this limited gravity in orbitals. Now here is a stock image of a lunar rover, but we stories from the Apollo 14 missions and previous missions about negatively affected due to the microgravity, and this can range from disorientation to reduced proprioception, decision making, and the proposed solutions that we'll touch on today, which are used now and quite beneficial, and something we'll definitely when we go to the moon and Mars, are lower body negative pressure chambers and prophylactic driving AI and VR mission route training. The last two are more theory, but they are using augmented reality with now for ISS missions or repairs. But we'll touch upon that in a second. So there's two main topics to go over as the main problems that affect people when they are taken to microgravity. So the first problem is so as you guys are sitting or standing now, you're being acted on. And if you stand up, like the image, notice, or perhaps you won't even notice, but in your body, physiologically, the fluid will be drawn towards the bottom. That's because gravity is acting to draw it all downwards. So you get a pressure gradient, which is lowest at the head and higher. And this is natural for humans. However, when you take a human this pressure gradient evens out, as you can see. So a steep curve on the left image is actually flat on the right. As you can see in the image, it says one of the big symptoms of this is, which can be quite surprising to the astronauts when they first arrive on the ISS. Now, we'll go into the topic of SANS. So SANS is SANS, and it's associated neuroocular syndrome. It's a mouthful, and I hate saying it, but it's a description of increased intracranial pressure due to this venous congestion in the brain. And what that means is because from the bottom of your body to the top, you have where there was less pressure initially. So all that blood, all that fluid in your legs is moving upwards into your abdomen, into your chest. And because of that increased pressure in the head specifically, of raised intracranial pressure. Now, some of you who are medical students might know the symptoms of this. For those of you that don't, the classic symptoms you think about are nausea. You can also get some fatigue with these patients. Is impaired visual perception. More specifically, that are closer to them appeared quite blurry. And imagine you're just entering the ISS for this first time. You've pulled the latch and you've entered. What's close?
I'm so sorry to interrupt, but I think we might be having some small issues with your audio, in terms of it just glitching a little bit. I'm not sure if it might be easier or better just to try without your camera on for a second, just to see if we can improve the audio.
I can turn it off now. How is that?
Yes, if we try that for a second, if that's okay.
Yeah, no worries. So I'll just go back over. So as you can see on the different pressure gradients, so when you're in microgravity, the fluid moves upwards into your chest and head. This causes symptoms of raised pressure, which include vomiting, nausea, vision changes in this case. Now, the vision changes affect your ability to see objects that are close and closer to you. So if you're put on that, weird experience and quite an unnerving experience. We also should talk about arterial stiffness. Now, this is exact mechanism isn't known, but we saw after the Apollo mission, the astronauts had an increased chance of death from CVD causes, disease. Now, like I was saying, the exact isn't completely known, but we have to consider these risks for everyone when we will touch more upon the long-term risks in terms of radiation. But essentially, this is what SANS associated neuroocular syndrome. It's the venous congestion causing raised intracranial pressure symptoms, which can really affect astronauts' performance on the ISS. In the first 2 to 3 days when astronauts go onto the ISS, around 60 to 70% experience one of these symptoms of nausea and vomiting and headaches. The topic that I'd like to discuss is altered input to the vestibular system. More specifically, your otoliths. Now, you don't exactly need to know 100%. It's a bit of a complicated topic, but essentially, the otoliths are small bones in your ear can detect acceleration, and they are sensitive to gravity. So, microgravity, these bones and these organs don't get stimulated. So, otolith deprivation, and this lack of input can negatively your proprioception, your balance, your orientation, and your coordination. So think about these two phenomena acting upon each. really creating an unstable environment for our astronaut to operate. We'll go to the next slide. Okay. So
Sorry, Cameron, we're having a few troubles with it glitching still. Um, is there a way for you to maybe rejoin just so we can try and get it a little bit smoother? Because I think some people are finding it hard to follow when we're missing a couple of words. I'm so sorry.
no, of course, I'll have a look around and maybe close some tabs.
Thank you so much.
Okay, should we try again?
Yeah, let's try again.
Okay, and I'll go back a tad. Can we see this?
Yep, we can see it. Fabulous.
Perfect. So I'll play this video first. And what this video is, uh, I'll show you first, and then we'll talk. So what you're seeing here is the Tesla algorithm. I'll see if I can pause this as that gets saved. Perfect. Here is an algorithm developed by Tesla in order to prevent any real bad crashes. And this was during the group project is that we could take a similar algorithm, the same machine learning, and implement it for lunar vehicles on the lunar surface. In a study on astronauts who had recently come back from the ISS simulator, and results showed quite marked decrease in driving ability and often swerving to the other side of the road and struggling to stay in their own lane. Apollo astronauts described it like being on a rocky ocean, driving across, because it really was unfamiliar environment in reduced gravity, and with all the impediments we discussed earlier, odds were just continuously stacked against them. So if we could an algorithm to develop something similar for the space, that could help us avoid craters or other serious collisions. We also should talk about the lower body negative pressure. So earlier, and you can see the woman on the right is wearing or holding, in fact, EMP suits. Now, to my knowledge, this was originally developed Russia for their cosmonauts. Essentially, how it works, you pop each leg into the trouser, and it forms a sort of vacuum around your legs and lower body, with the resulting pressure stimulating, being like a mock gravity suit for your body, which ends up drawing fluid back down from your upper body into your lower body, resulting in more into what we're normally used to for life on Earth. We could use this for about 45 minutes to an hour for about 6 to 7 days, and we see quite marked improvements in astronauts' behavior. What we'll also touch on is VR route training. Augmented reality and reality are becoming super interesting and useful tools that we in our space program in order to simulate missions, walks, EVAs, and simulate repairs that we need to do. So we'll go on to the next slide. So the picture on the left is meant to represent a model on the right. So on the right you have the ISS and a specific module. You have an astronaut. This is Johnny Kim. I believe he'll be going into space this year or next year as part of the ISS crew. He's using augmented reality plus reality as we know it, and reality with so the wooden blocks are meant to represent the chunk or the bulk of the ISS module that he'll be working on, and then the AR headset, as you can see, will be used to overlay the intricate details before we go into the mission as sort of a pre-preparation. So when they do the EVAs themselves, it's not as foreign. You may have seen videos or pictures that certain companies such as NASA and ESA with its own smaller one, but have a huge pool, and in the pool they have space modules. NASA actually has a one-to-one of the ISS where they can practice these EVAs and these spacewalks buoyancy, which is the closest that we can get on Earth to zero gravity or minus. So we're really always trying to constantly simulate these and expose these astronauts to as much of the microgravity before they get there themselves. So for this course, we an abstract. The abstract was one of the ways we get judged, whether we got accepted into the program. And there's a variety of topics that, if you go back to my first slide, there's essentially of what you can do your work on, where you see that astronaut and how each part of his anatomy is affected. I chose to do my abstract on microgravity immune system, something I found really interesting. A lot of people who program did their abstract on SANS, the space associated neural. This seemed a bit more niche to me, so I thought it might be a way. But we'll go over, we'll touch on this topic. So the key findings for my abstract was, as you can see, that microgravity essentially suppresses the immune system function. Microgravity is an extreme environment. Or over 50% of Apollo astronauts actually encountered a respiratory or or skin infection while on their missions. We need to think about how this will work for Moon and how this will work for where missions are 6 to 9 months. And then we also need to understand why. Why does this happen? So the theory is that extended periods in microgravity can cause cell, and due to this mislocalization in the cell, you have altered cell regulation and altered cell proliferation, and all this results in reduced proliferation and increased inflammatory responses. Now, the study where they had two twins and one twin spent a year aboard the ISS, and one twin on Earth. And they studied them both when they were both back on Earth. And the twin that had been on the ISS had increased inflammatory markers produced, showed more intense responses to what would be normal stimuli. So this posed a challenge for us to think about when an astronaut comes back to Earth, or from any space mission, how do we look after them so that they trust? We also need to consider the fact that the ISS is a sterile environment, and we also need to keep it sterile for our astronauts, which is a bit of a double-edged sword. The immune system hasn't been stimulated, and it's also harder for the immune system to resist and infections in the first place. So we need to countermeasure with potential and potential quarantine post-mission. One of the biggest challenges in any extreme environment, and especially in space, is mental health. We need to think about challenges. They're isolated. In missions to Mars, it will take months to get there. And to justify the missions, they need to last long. So we'll be thinking that the astronauts will be away for years, and even to get back in months. And even psychologically processing that as an astronaut, as a human, can be quite challenging. For the moon, it's days to get there and days to get back. And for the ISS, it's hours. Emergency capsule and take an emergency exit from the ISS takes around 4 hours. So the stakes are quite high, but even more so when we're on Mars and the moon, especially considering where the only imminently is with your crew. And go to Mars, it will take around 22 minutes for us to get communication back. So 22 minutes one way, 22 minutes the other. It's like an hour to get a full loop of communication. So psychological challenges, the isolation, the stress, and the sleep disturbance. You can see 16 sunrises and 16 sunsets a day. And this ruins your circadian rhythm, your sleep cycle rhythm. 3 is a perfect concoction for there to be stress in space and just real psychological challenges. And what we were learning about during this period, during these lectures, quarter phenomenon, which is a theory that suggests that the third quarter, any intense isolation period, is generally the hardest. It's when we enter into a quote-unquote psychological hibernation, and most mistakes occur during the mission, and it's where it's most psychologically difficult for the astronaut. One thing that we were being told about and we discussed during these lectures, because the person who delivered the lectures was actually a psychologist who worked for ESA, was that astronauts tend to underreport their symptoms. Their one chance, and because they don't want to be a bother, but that this really prevents mission progress and prevents the mission going as we understand that we select astronauts because of their resilience, but then it's also a balance between being honest and opening up and asking for help when they need it. But what are some solutions? So telemedicine. The psychologist has weekly meetings with the astronauts where they touch base, where they have conversations up and just check in. And if there's any problems that need to be addressed, they can do so. The support and crew morale. It's super important for the mission that everyone gets on, that the team morale is high, and that they can form a cohesive team. stressful working on the ISS. The timetable is quite rigid of time for yourself. So having a supportive group around you. And the last one is contact with family and friends. And asked about what they think about the most, these astronauts who are on the ISS, it's frequent their hobbies, their families, their friends, as you would expect. And so frequent contact with and still feeling like they're part of their lives is of the utmost importance to for everyone. Okay. Now, just going back to my experiences. So, as I was saying, the students ranged from Greece to Norway to Lithuania. It was a real mixed bag. And when we first got there, a tour of the place, we went to some space theme parks. We had a lot of pictures, and lastly, as a surprise for what I suspect is every, but we were told it was a surprise for us, was an interview with an astronaut, and we had an interview with Carmen Posnig, who was the 22 astronauts. She was one of the 20 astronauts selected out of applicants to become an ESA astronaut. Is a medical doctor. She specialized in ED, spent 1 year on Concordia Research Station, which is stationed in Antarctica. Similar circumstances to the ISS, you're isolated and in an extreme environment. There she was carrying out her own research and working for ESA there. But we also have other medical doctors who have joined ESA specialties. It's not just limited to emergency or acute medicine, because as you would expect, such an intense environment really calls for people under pressure. Okay, now I have some video from my experiences. So this was one of my colleagues. Yes, there we go. So this was a simulation, like sorts, which would simulate the moon's gravity, and you'll be able to see unnatural and how clunky it looks. You might in your head think it's quite easy to, but when you've spent your whole life and all of human evolution has gotten you used 1G gravity, going from that to something different can be quite the change. Not warps, but it really does show. And when I was using it myself, clunky and very strange. And think about how this can be compounded if you on the lunar surface with all the aforementioned problems, and vision is altered because of the fluid shift, and you're protected because of your vestibular system and everything that's going on. It's cool to work as effectively as possible. Now this, I will skip through most, but this is also a demonstration of a centrifuge. So this, and then I'll mute it. But what you can see here is a centrifuge spinning, and after 10 to 15 seconds, the floor for this apparatus goes down. You can see it moving down now. So what's sticking us? The wall is the force created by the centrifuge, and this is just a demonstration of gravity. Gravity, normal gravity, which causes us to stand still, but as when these pivot forces occur. expect that we could use something similar on the moon or on Mars, create more Earth-like conditions in order to draw the fluid back down and to create some more normal to counteract experiencing in space and create more of an equilibrium for our bodies. So there's that video. And the last video is is happens to the vestibular system. So the otoliths are those small bones, acceleration, deceleration, and can contribute to balance and this is a multi-axis unit which is designed on all axes and really throw you off. And if I remember, I felt sick for about 2 days after I was on this. Now, the key to this essentially is to have your gaze stationary object. So they have a piece of paper right in front of you that they ask you to fix your eye, which is meant to mitigate as much as possible the feeling of sickness but it recreates the feeling quite well to have feel, or most of the astronauts actually, when they get to the ISS, they feel nauseous, vomit, they feel quite out of it. Go to the next slide. So we've spoken about the main issues and we've spoken about how these can affect the human body. And now we're going to look at what are the space medicine on the Mars missions. The Mars is the end goal, the time for space exploration. We start at the moon, we come back, but from our talks, from our lectures, and from peers and supervisors, the impression we got was all eyes were really looking for and establishing colonies there. So, big one is radiation protection. Earth's protective ozone layer, we're exposed not too much, but to radiation and heavy ions. And these radiation and heavy up, as I was saying earlier, the mission to get to Mars will take 6 to 9, and to get back another 6 to 9 months. The consideration will be, is this a consequence we're willing to accept? And how do we protect the astronauts and the equipment while maintaining the space shuttle taking them there? So we need to think of some short-term consequences. Short-term, it's been theorized that this short radiation exposure, some neurological changes, but in the long term, issues with fertility, we're thinking about and we're thinking about cancer. These are the big issues that we have to consider, and we have to weigh up if the risks are worth the benefit and whether that's a are willing to take in order to carry out the mission. We all need microgravity countermeasures. Like I was saying earlier, the lower body negative pressure and potentially a short arm centrifuge on the space shuttle are going to be super important and to counter the microgravity and the effects of that while on these missions. And you may have seen before the big emphasis on exercise. They spend a day doing exercise and weightlifting in order to combat muscle loss that occurs. So it will be very minimal on these long haul trip. It will be trying to maintain the structural integrity of their body as much as possible. Once again, what we spoke about previously, telemedicine advancements and mental health. Traveling on a voyage, into the furthest from other humans that we've ever been before can be quite taxing mentally, and that our astronauts are in tip-top shape and have all the support they need in order to, and life support systems. If the worst should, how do we save life and how do we sustain life? In They have developed a form of CPR where describe this, I think, but essentially they push themselves off one wall of into the chest of the recipient and try and get chest compressions in that fashion. But we need to think about what we have and how can we use this medical equipment to save and preserve life if needed to. Okay. And then we need to think about life on Earth. What's the takeaway for people on Earth, everyday people? So I'm going to touch on a few. There's a lot of stuff we can go through, but I'm going to touch some topics I find quite interesting. So the improvement of remote areas. What does this mean? Ultrasounds, for example, have impact and much more remote as years have gone on, and this has really been the space program. All astronauts on the ISS are able to use it for diagnosis and investigation. Because this technology has been made so compact and refined, so you'll see it trickle down into hospitals now. You have super compact and super portable ultrasound machines, whereas in the quite clunky and quite a hassle to move around. With water, we can see here an astronaut growing a plant or one of the modules. When we'll go for water first. So on the ISS, you need using water filtration because you don't have any up there. There's no natural resource. You have urine. You need to have amazing water filtration, the water from the urine, and preserve life there. That has for Earth, where water might be polluted or dirty, and the technology we use in order to purify this water has interesting carryovers. And also air filtration. Once again, there's no oxygen in space. We need to think about how we're cleaning the air and how we're recycling the air for our astronauts to breathe and to be healthy. And the carrier of Earth is crops and food stores. So that this air filtration can really increase the longevity of shelf food and cause it to last longer. And so if there were ever any natural disasters, be preserved and food can be stored for longer and safer. The third point is artificial blood for animals. So there's, as you would expect, a real lack of donors for animal blood. Get your hands on, especially in case of emergencies, and that is due to lack of donation, yes, and due to the lack of albumin, which is the most common protein in the blood, and this is very hard to recreate on Earth. To make the crystallized, which we would need, it's very hard to recreate these conditions on Earth, but it's easier on the ISS and in microgravity, so we can study that and how we can get to this building stage, and then once we understand that much better, then we can get into animal products or animal blood products more specifically. Touch on was medical scanning technology. Now this was almost an accident where they were scanning neutron stars, and they were with an X-ray telescope. And I believe it was some doctors at the University of Massachusetts or hospital in Massachusetts that found out about this, realized that they could use it to create a much more localized and radiation producing CT scanner, which can be used to specific limbs as opposed to the whole body and expose you to much less radiation. It's safer for everyone in the long term, and especially safer for our astronauts to fit that onto one of our capsules. So just to recap, so space medicine is vital. Push the limits and explore our solar system, our galaxy, and the stars. Opportunities exist for students to contribute to this field. In this picture, these are student-led parabolic flights. So parabolic are essentially when you get a big plane, you take out all the seats, experiments, you fly the plane up a couple thousand, and then you fly the plane down at an angle. And what this does, for a few seconds, it simulates microgravity. So you're floating, and it looks super fun, but it's also super good to mimic the environment, experiments. So if this is something you want to look at more in the future, quite a few of my colleagues who went to this course with me ended up going on parabolic flight, out their experiments on it, and it seemed amazing. And there's always an intersection with your specialty of interest and space science. Didn't just have medics on our course, we had astrophysicists, biologists, we had engineers, we had a real mix of everything, and always intersection with what you're interested in and space science. This space physiology training course that I underwent takes December. So every year in December, applications or October, I think, but the actual course itself takes place in December. And just lastly, here's my email. If you have any questions or further talk or questions about application, just send me an email. I'll be more. Thank you for listening. That's the end of my talk.
Amazing. Thank you so much, Cameron. I'll give a virtual round of applause on behalf of our 97 attendees. Super, super interesting. Covered loads of different areas that I think maybe not everyone had considered or thought about. So thank you again for giving up your time.